We present positive-unlabeled reward learning. The goal of generative adversarial imitation learning, or GAIL, is to train a discriminator d theta that distinguishes between some expert demonstration and the data generated by enacting policy. By using this discriminator as a proxy reward function, the policy can learn to improve its behavior to better imitate the expert demonstration. This process converges when the discriminator cannot tell the difference between expert data and the policy data. However, in practice, the discriminator often tend to overfit and distinguish the two data sources by focusing on features that are irrelevant to the task. For example, subtle differences in environment lighting between the expert and agent data. This prevents the policy from further improving and often yields poor results on complex tasks. There have been many works on curbing the problem by regularizing the discriminator, for example, by limiting the capacity of the discriminator network. In this work, we take a different perspective. First, we notice that the simplest way to address this problem is to train a discriminator to classify whether the trajectory successfully completed a task or not, regardless if it comes from expert or the policy. However, this would require the privileged success and failure labels to learn the positive and negative classification. In practice, all we know is that expert data are successful, and we do not know the labels for the agent data. So in this work, we consider expert data as positive data and agent data as unlabeled data, and pose the discriminator learning problem as a positive unlabeled learning problem, and present positive unlabeled GAIL, or PU GAIL. Specifically, we base our method on a PU learning formulation that works well with complex function classes such as deep neural networks by imposing a non-negative constraint on the original PU learning formulation. We adapt the GAIL discriminator objective with a non-negative PU learning objective and call our method non-negative PU GAIL. Our method is a drop-in replacement to the original GAIL algorithm. We evaluate our method on a standard benchmark Walker task and two challenging tabletop manipulation tasks. We compare our NN-PU GAIL with three baselines, including PU GAIL without a non-negative constraint, vanilla GAIL, and a GAIL regularized by input image augmentation. We see that all four methods perform well on the standard Walker task. In lifting, both PU learning methods perform better than GAIL, and in the most challenging stacking task, NN-PU GAIL is able to outperform all baselines with wide margin. In this paper, we also show that we can address a different learning setup called supervised reward learning using a PU learning formulation. Here we assume we're given a set of data, each labeled with some reward value. We can train a supervised reward model using these data and train a policy using the learned reward model. The reward prediction can be accurate when the policy data are close to the labeled data. However, the agent can go out of this region and arrive at states for which reward prediction is unreliable, where the agent may get high pseudo reward for unintended behaviors. For example, here, the agent tricks the reward model to give it high reward by posing as walking but not actually moving. This is known as the reward delusion problem and is known to cause safety concerns in real-world policy learning. We show that we can use PU learning formulation to address this problem. We can think of reward labeled data as positive data, meaning that the reward prediction made on these data are likely reliable because they are the training data for the reward model. On the other hand, we do not know which data points among the policy data are unreliable, so we will consider all of the policy data as unlabeled data. So we can train a classifier using an NNPU objective and suppress the unreliable predictions made by the supervised reward model, and we call this non-negative positive unlabeled reward learning. Here, we visualize how our method can suppress the unreliable reward predictions on a lifting task. This is a policy trained with a basic supervised reward model. You can see that it tries to get high pseudo reward by moving out of the camera view, and our method is able to suppress the unreliable reward prediction as soon as the object moves out of the camera view. We observe similar behavior on a stacking task where the policy tries to occlude objects from the camera view to get high reward, and our method is able to suppress the reward prediction on this behavior. Here we show quantitative results. PRL is the basic supervised reward model, and PNRL is with the positive-negative classifier. We see that both PNRL and PRL plateaus at low performance in Walker and stacking, and our method, the green curve, is able to outperform all other baselines in both the lifting and stacking task. Finally, we show that our method can handle domain shift, created by collecting supervision data and learning policy with objects of different dimensions. We see that in both adversarial imitation learning and supervised reward learning settings, our method is able to outperform baselines with a large margin. Thanks for watching.